Okay, time for another look at duration. We've already computed Macaulay duration. We've done examples on the calculator for modified duration, the conversion to Macaulay, and then I showed you in the previous video that old school way of doing modified duration again. And I just want to talk a little bit more about the application of duration so as not to get too carried away with how to compute it, but actually think about how to apply it. Please always remember that what modified duration is telling us is the anticipated percentage change in bond price, but importantly we're talking about its full price, also known as the dirty price. So in the case in cases where you've got a bond that is in between coupon payment dates, that means clean price plus accrued interest. So percentage change in the bond price, its full price, for a 100 basis point change in yields. If interest rates go up or down, or yields go up or down by 1 percentage point, 100 basis points, what will happen to the bond price? Now, as we will be exploring in a lot more detail later on when we talk about the convexity adjustment, what duration essentially tries to measure or show us, portray, I didn't want to scale in, is the following. Let's draw a simple chart where we will have on the one hand bond price, and on the other hand yields. And as we hinted on before in a much earlier lesson, the relationship between the two is inverse, but it's not linear. It's a convex curve. Okay, that's more or less convex. So what duration tries to tell us is pretty much the slope of that curve at any given point in time. And that curve, it changes depending on whether you are currently here or up here, you know. So for a given level of yield and price, what will happen if yields go up or down? What will happen to the price in terms of it going accordingly down or up? However, duration is just a single measure at a point on this curve. So it tells you what will happen when yields, for example, increase a bit or decrease a bit by telling you, well, the price will either go down or up accordingly. It doesn't really account for the full difference because there's also that thing called the convexity adjustment, which we'll be doing later on, which allows you to approximate the full extent of the change. There's an upward adjustment. So duration is just a linear measure. It's the slope of the function. It's an approximation of the price change. It doesn't give you the real price change, but that's what it's meant to be. So just a bit of context to add to this discussion. Now we've got a little bit of a question which will apply the duration logic. A 3.5% semi-annual coupon bond has an annualized Macaulay duration of 4.2. I told you in the earlier video that durations are always going to be annualized when given to us. If the bond currently trades at an annualized yield to maturity of 4, once again, yields are always annualized, even if bonds are pay coupons semi-annually, as this one actually does. The anticipated change to its full price if yields decrease by 50 basis points is closest to. Okay, so we've got a bit of context which we can put on the graph above. The current yield to maturity is, for this bond, 4%, and we're asked to anticipate what will happen if yields decrease by 50 basis points. So they go by half a percentage point that way to just 3.5%, I guess. Well, of course, the price will increase. There's no other way kind of to think about this. The price must increase, so it will either be answer A or B. It cannot be any other way. The question is, which one? Now, let's make use of the relationship that we already know. Annualized modified duration equals, well, whether it's annualized or not doesn't matter, equals Macaulay duration, also annualized, divided by 1 plus R. But I told you before that R has to be scaled down. In the previous video I kind of emphasized it. This is the yield per coupon period, and in the previous video we had a very big yield, 60% annualized, which we scaled down to 30% per semi-annual coupon period. Here it's going to be less extreme, so we're going to have a Macaulay duration of 4.2 from up here that I'm going to divide by 1 plus, now take the 4 and scale it down by dividing by 2 to a semi-annual period, so 4% divided by 2. Let's see what we get on the calculator. 4.2 divided by 1.02, this gives 4. Well, more or less 4.12. Okay. Now, what does this mean? The percentage change to the full price of the bond. The price of the bond is typically denoted in your curriculum as PV, the present value, but the full price of the bond is approximately going to be the annualized modified duration, 4.12, but because when yields change, we have an inverse change to the bond price. So if yields drop by 50 basis points, half a percentage point, then bond prices go up. I'm going to stick a minus here and say annualized modified duration, which in our case is simply this 4.12. So take the 4.12, stick a minus in front of it, multiplied by the change in annualized yield. Now the yield here goes from 4 to 3.5, so 50 basis points, and you've got to express, or you can express, or how you express this is kind of your thing. I like to express this in decimal format, so say times 0.005. That's half a percentage point. Although you could do it differently, you could do it as 0.5 and just remember that this is done in the relevant units. So 4.12 times 0.005 of course gives 0.0206. So 2.06%. But if you wanted to, you could just as well have written minus 4.12 times half a percentage point, and of course that would give you 2.06 anyway on the display. So just be aware of the units you're using. It's up to you, don't get confused. So 2.06 increase. Now I wasn't very mindful of the units. Yields were dropping, so I should have had a minus here, a minus here, and a minus times a minus always produces something positive. That's the thing I forgot because I was carried away doing the explanation of the units, but you get the idea, hopefully. It's answer A, a 2.06% increase. Right, now for the next question which I want to do with you, and this one is all about something called approximate modified duration. You kind of know already that you can easily compute modified duration once you know Macaulay duration, and your calculator will help you compute Macaulay duration quite easily. We've done that in previous videos. Now, sometimes it may not be possible to really compute Macaulay duration, and it's not because you've left your calculator at home and you don't have access to it. It's because a bond may contain certain built-in features, embedded options such as call or put options, which will make it problematic to compute Macaulay duration. So let me just write down that computing Macaulay duration is problematic, or may be problematic, for bonds with built-in options and in that case it's going to be a better idea to use something called approximate modified duration, which is what this question wants us to do. Let's have a look. A bond with 3 years to maturity pays an annual coupon at 6% of par value and trades at a yield to maturity of 8%. Now, this is pretty much the same bond that I used in the previous video on the light board, where I computed modified duration from start to finish going via Macaulay duration. But this time I'm going to try and attempt to do a computation of approximate modified duration using a 50 basis point change in yield assumption. Now, what's all this about? I don't think you'll have to do this in the exam because, to be honest, approximate modified duration will come in very close to modified duration, so there's no point testing this. You just have to know the concept more or less. What you need to do is the following. This is our convex relationship between the price of a bond and the yield. Now, I said just a moment ago that this really makes sense. Doing this computation really makes sense when you've got bonds with embedded options. Well, this one doesn't, so it even more doesn't make sense, but you just have to understand the concept. What we're going to do is check what the price of the bond would be given its parameters. It's a 3-year bond, it pays a coupon at 6%, and initially it trades at a yield to maturity of 8%. So if, let's say, this is a yield of 8, let's figure out the price of this bond, and I'm just quickly going to do this on the time value of money worksheet. Clear it, second FV, and input the relevant data. So we've got 100 for FV, 6 for the PMT, the coupon, 8 for I over Y, it's an annual coupon bond, right? 3 for N, and let's compute PV. Well, the answer is 94.845. Okay, let's think about what would happen if yields went up a notch by 50 basis points. So they would go up to a fresh level of 8.5. Now on my chart that looks very extreme, but it's probably not as extreme as I'm making it out to be. Well, let's recompute the price. The only parameter I need to change is the YTM, or the I over Y parameter, so I'm overriding this, compute PV again, and I see a fresh price of 93.615. It is indeed lower, just a bit, and this is the price for a yield increase. So I'm going to label it as the PV plus because yields went up. And same thing if yields go down 50 basis points to 7.5. As you can see, because of the convex nature of the curve, we get a bigger increase in bond value when yields drop by 50 basis points than when the yields go up by 50 basis points. The change, the magnitude of the change is different. Okay, 7.5, substitute that for I over Y and recompute PV, right, 96.099. Now, the thing is, your calculator says You now know what this point is, you now know what this point is, kind of you know what the prices would be under both scenarios. So let's, in a way, imagine that we connect these 2 points with a straight line and we measure its slope, because that indeed is going to be the slope of the curve at this point, more or less. That's what approximate duration, approximate modified duration is. So our annualized, they always talk about, well, in this question they don't, but in reality you'll often be asked about annualized approximate modified duration. The fact that it's approximate means it was computed using this way rather than the sort of the classic let's compute weights, weigh each time to recede by the relevant weight, etc., etc. This is the price of the bond when yields went down, so PV with a little index minus, PV index minus PV under the scenario where yields were assumed to go up. Okay, so what we've got effectively over here is an expression for this horizontal distance. And, if you are trying to compute the slope of anything, a line going from here to here, you have to start with that vertical distance, and you definitely need to divide by the horizontal distance as well. So I'm going to do divide by, and look, that horizontal difference is 2 lots of 50 basis points, one way and the other way. So we effectively have over here in the denominator an expression that's going to be 2 times the change in yield that we assumed in our computations. That's going to be, in our case, 2 lots of 50 basis points. And, because we are doing, after all, some form of modified duration, approximate or other, it doesn't really matter, we are thinking about the percentage change in bond price. So we have to relate everything to the starting bond price, which was our PV0 over here. It started to look as an 8, like an 8, so that's our PV0. So I'm still going to divide over here by my PV0. In fact, in all the formulas, this may appear at the beginning of that denominator expression. I've done it at the back. It doesn't really matter where it's multiplication, so the order is not important. Let's plug the numbers in. For PV minus, that's the higher number. I've got 96.099. That's obviously the price of the bond, assuming a yield decrease. I'm going to deduct the price of the bond, assuming a yield increase. That's 93.615. Okay, divide by 2 lots of 50 basis points, so 0.005. I like to express this in decimal format, and multiply in the denominator also by the starting PV0, so that's 94.845. 94.845, and let's see what this gives on the calculator. So let me get my recording started on the calculator. Here we go. Right, 96.099 minus 93.615 equals, and divide all of this. I'm going to open a bracket by 2 times 0.005 and multiplied by 94.845. Close the bracket. What do we have over here? We've got an answer of 2.62 approximately, and that is very much in line with answer A to this problem, 2.62. So that's approximate modified duration for you. It's annualized. If you ever need to compute it, this is the way to go. In reality, you'll typically rely on your bond worksheet on the calculator to do most duration computations.